Variation of parameters is a second method for solving second-order differential equations when we have a forcing term on the right-hand side. In other words, it is a non-homogeneous differential equation. So here's a particular example: y double prime minus 5y prime plus 6y equals t e to the 2t. So in this case, what we have is a second-order linear differential equation with constant coefficients, and we have on the right-hand side t e to the 2t. Well, just like we did for the method of undetermined coefficients, we first solved the corresponding homogeneous differential equation. That would be y double prime minus 5y plus 6y equals 0. The characteristic polynomial would be r squared minus 5r plus 6. If we set that to 0, it actually factors pretty nicely. R minus 2 times r minus 3 equals 0. So that means that our fundamental solution for the homogeneous differential equation is c1 e to the 2t plus c2 e to the 3t. So one method to solve the non-homogeneous equation would be the method of undetermined coefficients. Unfortunately, what we have here on the right-hand side, t e to the 2t, is not something for which undetermined coefficients would work, at least very easily. If we had just t, we could solve using undetermined coefficients. If we had just e to the 2t, we could solve using undetermined coefficients. But when we have a product like this, t e to the 2t, it's a little bit more difficult. So that's what variation of parameters is about. It's about certain situations where the right-hand side involves a function of the type for which undetermined coefficients would not be appropriate. To use this method, we're going to have to use the Wronskian. So if you'll recall, the Wronskian of the second-order equation is e to minus the antiderivative of p. In our case, p is negative 5, so we have e to the antiderivative of negative 5. The negatives will cancel. The antiderivative of 5 is 5t, so the Wronskian in our case is e to the 5t. We're going to use that in the subsequent calculations. Now, in Boyce and DePrima's book, section 3, theorem 3.7.1, there's really a formula that allows us to get our particular solution. I won't go into the derivation of this. It's a generalization of what we do for the homogeneous situation. But the bottom line is that once we have our fundamental solution to the homogeneous, y1 and y2, we get our particular solution by taking minus y1 times the integral of y2 times g. Now remember, g is the right-hand side of our differential equation. All of that's divided by w, the Wronskian, plus y2, and then we take the integral of y1 times g over the Wronskian again. So once we found the solution to the homogeneous, what we need to do is we need to calculate and simplify that quantity, and hope that we can actually integrate what's remaining. So taking a look at this example, we saw that y1 was e to the 2t, so we have minus e to the 2t. y2 was e to the 3t. G of t, the right side, was t e to the 2t. And then we computed the Wronskian on the previous page. That was e to the 5t. And we can see how this is going to simplify pretty easily. We'll have e to the 5t in the numerator, e to the 5t in the denominator. So this whole thing will be reduced just to be the integral of t, which I've written down right here. Now on the other hand, y2, e to the 3t, y1, e to the 2t, g is t e to the 2t over e to the 5t. Now in this case, we're going to have a leftover exponential because we're going to have e to the 2t times e to the 2t, which is e to the 4t. E to the 4t divided by e to the 5t is 1 over e to the t. So I'm going to have the integral of t over e to the t, and we can change this t over e to the t to something of the form t e to the minus t. So at this stage, the first term simplifies to be just minus e to the 2t times the integral of t, which is minus e to the 2t times the antiderivative of t, which is t squared over 2. We don't need to worry about any arbitrary constants here because that all gets factored into arbitrary constants at the very end when we write down the solution to the differential equation. And then we have e to the 3t here. And if we simplify this integral, t over e to the t, we have to integrate t e to the minus t. This integration is going to be a little bit more painful because we have to use integration by parts. So here's the first term from the previous page, plus e to the 3t. We need to now integrate this by parts. U is t, u prime is 1, v prime is e to the negative t, v is minus e to the minus t. So I'm going to write this first term again right here, e to the 3t right there, and I'm going to put big brackets because I don't want to lose any exponentials or signs. So I have u times v, that's minus t e to the negative t, minus the integral of v times u prime, which is 1. So you see how I'm going to have two negative signs cancel here. So what I've done is I've written basically what we have above, except I've just canceled these two negative signs out. Now I have to integrate e to the minus t. That's a simple substitution, which yields minus e to the minus 2t. So the antiderivative of e to the minus t is what we have right there. So this will be minus e to the 2t times t squared over 2 minus t e to the 2t. And then I've got e to the 3t times, or there's going to be a minus sign here, and e to the 3t times e to the 3t times minus e to the minus t. We'd subtract our exponents, we'd get minus e to the 2t. So minus e to the 2t is the result of all this right here. So let's write down our final solution. We've got the solution to the homogeneous, c1 e to the 2t, plus c2 e to the 3t, that's the solution to the homogeneous, plus the solution to the non-homogeneous that we discovered using variation of parameters, minus e to the 2t times t squared over 2 minus t e to the 2t minus e to the 2t. This whole method is a bit more involved than the method of undetermined coefficients, in large part because we need to calculate the Wronskian. And we need to calculate the Wronskian, then do a whole bunch of integration as given by this formula. But it is a method that works, in particular when the function, the forcing term g of t, is not something for which undetermined coefficients works.